Welcome back, physics fans. This is question number 1 on page 98 from the workbooklet. So in this picture down here, how much work is done to stretch the spring from a starting stretch of 0.2 meters to a new stretch of 0.4 meters? So this is our force distance graph of a stretched spring. It follows Hooke's law, which is F elastic is equal to Kx. That's Hooke's law, that it's a direct relationship, okay? And we can even calculate from this graph what K is, because from this graph, when we pull with 6 newtons, it stretches 0.5 meters. So if we have 6 newtons of force is equal to K times 0.5 meters, this K is going to equal 12 newtons per meter. So from the graph, we can get the spring constant. It's the slope of the graph, by the way. Rise over the run will be the slope. Now, how much work is done to stretch the spring? Now, the work on a force distance graph, is the area. Okay? But they're not saying the area of the whole thing, only from point 2 to point 4. They want this area. So there's 2 ways to calculate that, maybe more, but there's 2 ways to calculate it physically, just right now count all those squares and figure out what that is, or figure out what this is and figure out what that triangle is and find out what that box is and add it together. It's that area. Or we can get this area, the work at 0.4, and then the work at 0.2, and subtract them. Okay? Because we want this blue area is the work at 0.2 meters, and this bigger triangle will be the work at 0.4, and then we can just subtract them. And that area is a formula. Okay, that area is 1/2 base times height, because it's a triangle. So the work, which is the energy in the elastic spring, is 1/2 base, which is the x value, how much you stretch it, times the height, which is the force. And the force is just kx. So if we plug that in, we get the elastic energy is 1/2 kx squared. And that's your elastic energy formula coming from this graph. We could have looked up on our formula sheet, and it's there as well. So we're going to just, the work to move it from 2 to 4 would be the elastic energy final minus the elastic energy initial, and that'll be 1/2 k, final is 0.4 squared, minus 1/2 k and 0.2 squared. So we can now that we also know what k is, we can plug it all in, and we'll get 0.5 times 12 times 0.4 squared, and that'll be 0.96 joules. And what does that represent? That's the big triangle. I'm going to erase it here, but that's the area of that triangle there, which you could have eyeballed the number off of there and done it by 0.4 and just did it yourself. That would have been close to 5 times 0.4 will be 2 divided by 1/2 is close to 1. We got it, close to 1. minus, and then do that again. The 0.5 times 12 times zero point 0.2 squared is the other energy, which is 0.24 joules. So then we just got to subtract them. That 0.24 is this blue one, 0.24 joules. So 0.96 subtract 0.24 will be how much work it will take it to go from 2 to 4. And that'll be 0.72 joules. Okay, lots of learning here. We could have done it by just looking at this graph and measuring it, the area out. Okay, we could have also did it as the area of this trapezoid. If you knew your area of a trapezoid formula, that height plus that height divided by 2 times the base would have given you that answer as well. Subscribe, like, comment,